Hello, everyone. Welcome to our live session. We are excited to be here with you this December 15th. So this will be our last live session before the new year. My name is Matthew. I'm one of the course instructors and course developers, and I will be taking your questions. For those of you who are new to the live sessions, we will explain how they work. So post your questions in the chat. I will grab them from there. Please ask your questions only once. We see all of them, but we try to go in order, but we also tend to jump around to make sure that a variety of participants get to ask questions and a variety of topics get covered. If you have not, make sure you like and subscribe to our channel. Click that bell icon so that you hear about upcoming live sessions for the new year. Chris, I'll let you just welcome everyone, and then we'll get started with questions from our participants.
Okay, thank you, and welcome everyone, whether you found us through one of our online classes or MOOCs, or just found us otherwise on the internet. Welcome, and I'm ready to take questions on pretty much any topic in astronomy.
Excellent. Our first question is from one of our live participants. IAC Tutorials asks, hello, sir. Why were constellations made by the Greeks? So many people have so different answers. Could you elaborate on why the constellations that we know are Greek constellations?
Sure. I mean, constellations are, just to frame the question, are patterns of stars that don't represent a physical grouping in space. So when you look at something like the Big Dipper or Orion, the stars that can join the dots to make a constellation are at quite different distances in space. I mean, quite severely different distances. In other words, they're not close to each other in three-dimensional space at all. They're just close on the plane of the sky. So there's no physical significance to a constellation. That's the first thing to say. Many of our current modern constellations in the Western world do originate with the Greeks, and that's just a function of history and Western civilization, if you like. But other cultures, of course, were seeing the stars with the naked eye going back tens of thousands of years, and they had their own constellations. So there are constellations that have been written about in other parts of the world that are not the same as our constellations. So that's the first thing to say. There's not a unique set of constellations. The modern set of constellations, I think is 118 or maybe 122, was codified by the International Astronomical Union maybe a century ago. And so it's been pretty stable since then, and it includes all the familiar ones, you know, the zodiac, the zoo of animals is the 12 constellations that sit around the ecliptic. They're the most famous ones. They're the sources of designations in astrology. But of course there's 100 other constellations, and many of them are quite obscure and most people don't know them. So constellations have a long and rich history. There's, for instance, the Big Dipper, is a constellation that has been written about for thousands of years, 5, 7, 8,000 years, so actually going back well before the Greeks. So certainly there's historical record of constellations that predate the Greeks. It's not like they were the first to invent even some of our modern constellations that we still talk about. It's a rich subject with a lot of history and a lot of culture, so it's one of those things worth reading about or learning more about.
Excellent. The next question is from another one of our live participants. Dark Reality says, I'm here. I don't know if they're new here, but they want to know how to get started on studying astronomy. We can talk about our courses, but there are probably other ideas that you have.
Sure. I mean, our introductory course, our course on Coursera, also Udemy, Coursera one's a little more recent, is a good survey of astronomy. It's an overview. It has all the topics. And that's a good place to start. There are other MOOCs and online courses. There are books about astronomy, popular books. There's Neil deGrasse Tyson sort of rebooted the Carl Sagan Cosmos series, and the book associated with that, with Cosmos, with Neil Tyson as the host, is a really nice overview of astronomy, and it's very colorful, good pictures and so on. It's a coffee table book essentially. So that's certainly one I would recommend. And then I would recommend just checking out astronomy in the journals like the Sky and Telescope and Astronomy Magazine, which both you can get print or online, and looking at astronomy as it occurs in the media. NASA's website is actually pretty well configured, and there's a ton of astronomy and space science on NASA, not just the missions they run, but explainer pieces that talk about astrophysics and astronomical phenomena. So NASA's a sort of go-to place. And then you might want to bookmark some of the major observatories of the world, because they have press releases pretty much weekly, sometimes more often than that. They also have incredible image archives and resources. And so that would be, you know, Kitt Peak Observatory, the European Southern Observatory, and pretty much any of the major optical or radio observatories.
The next question is from Johan Snepvanders, who asks, imagine a habitable planet with half the gravitational pull of Earth. Are the living beings on that planet on average twice as long as on Earth? Like, how would it change? How would the living beings change, with a planet that's half the gravity of Earth?
It's an interesting question, and we can speculate. It's a question sort of biology as much as anything. This is close to the situation of Mars. I think Mars' gravity is 38% of the Earth, so it's a little less than half. So what would creatures that evolved on Mars look like? It's uncontroversial to speculate that if creatures evolved from microbes to larger organisms on a planet with small gravity, they could indeed be taller, because it's gravity that keeps animals to a certain size. In fact, the maximum size of animals on the Earth in history, the largest dinosaurs, the sauropods, was pretty much driven by gravity and the tensile strength of bones subject to compression for many tons. And so dinosaurs couldn't have got much bigger than they were, the biggest of them. And on a Mars-type gravity or half-gravity planet, they could grow much bigger. So yes, it's a fair supposition that the animals would grow bigger. A lot of the other attributes will depend on the nature of the atmosphere. If the atmosphere was thicker or thinner, independent of the gravity, it would affect how, for instance, birds and insects operated, because they work within the aerodynamic constraints of the atmosphere and the air. So there's a lot of attributes of a planet that affect the type of life that might evolve on it.
Excellent. The next question is from Pinoclean, who asks perhaps a sci-fi question. Imagine if we could build a particle accelerator on the scale of a microchip. How useful would it be, if at all?
Miniaturized particle accelerators, they do exist. So there are not perhaps on the scale of a microchip, but certainly the scale of a lab bench, something that fits inside a lab, maybe a few meters or a meter long. It would be very useful indeed. Now, normally particle accelerators need some substantial distance to accelerate particles to very close to the speed of light, and they use magnets to do that, injecting particles with a certain energy and then accelerating them beyond. The technology that's used to create acceleration on very short physical scales involves either laser or plasma pulses. So you basically create a set of plasma pulses that capture or drive the particles very quickly to very high speeds, and so you can do it in a very short distance. And so plasma pulse accelerators do already exist, but not on the scale of a microchip. If you had such a capability, it would be very useful, because high energy particles are used for experiments in irradiating things and seeing how they behave. Treatment of cancers, for example, is a medical use of high energy particles from accelerators. And you could do a lot of just standard physics things that don't require the enormous infrastructure of one of the world's great accelerators. If you could do it on a small lab bench scale, then any physics department presumably could have an accelerator.
Excellent, thank you. The next question is from one of our online participants as well. Bernard asks, could the recent discovery of very early galaxies in an unexpected level of development lead to questioning the validity of the Big Bang model?
We've had this question, variations on it before, and the simple answer is no. The formation of galaxies quickly after the Big Bang and their growth to maturity and large mass, and even with large central black holes, is a challenge to formation of the theories of formation of galaxies. It's not a challenge to the Big Bang model itself, because the evidence for the Big Bang model is not impeached by these observations. What it is suggesting is that we don't really understand how galaxies form and grow. We assumed until these observations that galaxies grew in a hierarchical way from smaller pieces merging to form bigger pieces, and over time growing to large size. And that takes time. The hierarchical merger scenario for galaxy formation and evolution just takes a while to play out, billions of years. Instead, we have a situation where in 100 or 200 million years, we need to grow something about as big as the Milky Way, and that's challenging. It's not that it can't happen, and so simulations have shown that it is possible. You can arrange the situation, perhaps with early overdensities, which will fluctuate, and so you just pick a place that happens to have a high initial overdensity, then you can form a bigger object more quickly in that region of space. So not a Big Bang buster, these observations by any means, but definitely challenging our simple and maybe naive ideas of how galaxies form.
Excellent, thank you. The next question is from Terry Trevino, who sent an email. I love everything that the team does. Thank you and happy days of cheer. Their question is specifically about a paper that was published in Nature Astronomy that mathematically validates the idea that Enceladus may be undergoing active chemosynthesis. Could we expect that in nature that we will locate similar conditions for example, in the TRAPPIST system, or is our system still an anomaly with some of these outer moons and planets?
We have to imagine that big giant planets in exoplanet systems will have moons because it's a ubiquitous feature of our solar system. All the four giant planets have moon systems. Jupiter and Saturn have dozens of moons each, and Enceladus is one of the moons of Saturn, and it's quite a small moon. And so since Enceladus seems to have many of the ingredients for life, and it has geysers and jets and hot spots and an interior liquid ocean of some size, that does raise the possibility that such worlds exist elsewhere around exoplanet systems. The problem is that detecting an exomoon, that is a moon around an exoplanet, like in the TRAPPIST system, for example, where there are 4 planets that are ostensibly in the habitable zone of their star, is really challenging, and it's not really successfully been done. So we're not in a position to study exomoons yet.
The next question is from Kristen, who's on with us live. What, if any, alternatives to rocket fuel, hydrogen, oxygen, can we expect to see research and development on in the next few decades?
This is an important question because rocketry has not progressed dramatically or fundamentally since Robert Goddard in the late 1920s. That's a century of liquid fuel rockets based on chemical energy. So the way to go to larger energy concentrations and larger accelerations, and the way to leave the solar system, for example, would be to go beyond chemical energy. Hydrazine is one of the most volatile fuels that's routinely used by NASA, if not by the main private space companies. And so to do that, there are technologies that exist, and some of them have been known for 50 or 60 years, but we've just never had a big demonstration of their capability. You can use rocket engines that work on plasma, accelerate plasma. You obviously, hypothetically, could even make a rocket engine that is based on fusion and uses the power of fusion in a blast plate to deflect the energy and the momentum and therefore propel the rocket forward. So you could use fusion power. That's, again, beyond our capabilities on Earth, and so we haven't done it in space. And then in the most extreme visionary version, which is not decades but centuries probably, we could have an antimatter energy source, which is the most efficient possible energy source for a rocket.
The next question is from Hernan Reyes, who sent an email but is also on with us live. His question is about SETI. This is was on the 15th of December of 1612 that the Andromeda galaxy was first seen through the telescope by a German astronomer. Does SETI search for signals from Andromeda, even though it is 2.5 million light years away? What's the point, or what's the benefit of looking someplace like Andromeda for a signal?
Well, it's a bit of a stretch, of course, because most SETI is conducted on relatively nearby stars, because we figure the signals are going to degrade, any signal, unless it's extremely well focused, will decline with the square of the distance, inverse square law. So, more distant sources are just weaker, and the transmitter would have to be correspondingly more powerful. The opportunity of Andromeda, of course, is that you've essentially got 1 trillion stars. And there is a project out of UC, University of California, I think Phil Lubin is the PI, called the Trillion Star Project M31. And he has an idea, and he published this some years ago and is doing it on a small scale, to look for pulsed optical emission, essentially highly pulsed lasers coming from a civilization in Andromeda. And that technology, scaled beyond what we're capable of, but not to implausible levels, could momentarily, for short periods of time, rival the brightness of the entire galaxy. And of course, you're looking for that signal from 1 trillion stars all at once, because the whole galaxy is in your field of view. And that's why I call it the Trillion Star SETI project. It has a radio counterpart that's also been going for a number of years as a test bed. It's not a full-scale experiment, I would say. To also look for radio signals, SETI radio signals from Andromeda and M33. So yes, SETI is actually using the opportunity of simultaneously viewing stars to look for artificial signals. The distance, however, is so prodigious that in the parlance of Kardashev, this would be a type 3 or type 4 civilization, so an extraordinary civilization, one that could harness a significant fraction of the power of a galaxy to be able to create a signal that we could see so far away.
The next question is from Kirsten, who's on with us live. What are your thoughts on the recent paper that was published that claims that, or explores the possibility that singularities inside black holes do not exist after all?
There's a lot of theoretical speculation about black holes. This paper has achieved a lot of attention, but I should just point out that if you go into the archive in the preprint server, you will, in physics or astronomy, you will find 150, maybe 200 papers a year on the physics of black holes, including the singularity, the event horizon, Hawking radiation, and so on. So a very active theoretical field. And all speculations about the singularity are just that, they're speculation, because the event horizon is a shield from our viewing what's inside. In fact, Penrose and Hawking in the 1970s came up with a series of singularity theorems, one of which was there would be no naked singularities in nature. In other words, singularities would always be hiding behind event horizons. And this new work is essentially potentially refuting that contention by Penrose and Hawking, but it's very difficult to confirm it.
Excellent, thank you. The next question is from Tom Vassos, who has a thought experiment. If we assume we know for sure that the universe is currently infinite in size, does that mean that the universe was infinite in size at the time of the Big Bang?
That's an interesting question. Not necessarily, because the Big Bang was essentially the unfolding of space and time from an origin event that was formally a singularity, so just an infinitesimal patch of space-time. And the expansion of that space-time took place incredibly rapidly, much faster than the speed of light early on, especially due to inflation. So inflation guarantees that the visible universe is a small fraction of the physical universe. And how small a fraction is not clear from the theory. It could be an enormous factor. Now, is the distinction between the physical universe being 1,000,000 times larger than the visible universe enough to call it infinite? Maybe not. I mean, infinite universes don't really make physical sense, as Newton found out. So I think the speculation about an infinite universe is not useful, because it's a physically problematic concept. But certainly the universe could be so vast compared to our ability to observe it that for all intents and purposes it's infinite.
Excellent. The next question is from R. Moser, who asks, what's the current status of government military space programs, and can we expect science spin-offs of those military programs?
Potentially, yes, but in practice, probably no. The military has its own objectives, its own ways of operating, and there's a little bit of a firewall between what can be very secret military missions and what the civilian scientific sector can work on. So it's not just a question of a scientist getting top secret clearance to work on one of these projects. It's just a question of whether the technology is even transferable. The military, during the era of the space shuttle, realized it could not rely on NASA to launch its capability. And so the military developed its own launch capability. It developed its own space plane, a sort of small version of the shuttle. It develops its own rockets that can get into Earth orbit and carry humans to Earth orbit, just as NASA is doing with Artemis. So the military has a sort of parallel set of capabilities. And there's very little interplay between what the military is doing and what the civilian sector is doing.
I will also say that various scientists, including Freeman Dyson, have criticized military programs that keep themselves away from science because when they work together, and they tend to make both sides tend to make progress much more quickly. Like Star Wars in the 1980s actually slowed down scientific progress. I'll post a link from our video on that. The next question from one of our live participants is from Nader Alemi, who asks, does the sun's speed change when it collides with the galaxy's gravitational wave? So it sounds like there's a little confusion there. So does it change when it collides with a gravitational wave? But then perhaps you can also talk about when it collides with the galaxies, like arms, gravitational waves from the arms.
The gravitational wave energy is significant, but it's basically ripples in space-time. So gravitational waves do not typically provide propulsion type force to a star and therefore change its motion or direction. They will just be squeezing and then letting go, a rarefaction wave, space-time, including the space-time that the star occupies. So there's really very little physical influence there, apart from the sort of stretching and compression as the gravitational wave passes over at the speed of light. For the sun or another star in the Milky Way galaxy, the sun is in a very low density region outside a spiral arm between the Cygnus and the Orion arms of the Milky Way. And so the sun is not in a position or in a trajectory where it's going to collide with any significant density in the Milky Way for millions of years.
Excellent, thank you. The next question is from TJ Richardson, which asks, hi there, everyone, or howdy, y'all. Is there any legislation to protect dark sky areas?
There is. It's a tricky thing to do, though, because these dark sky areas are scattered around the world. Tucson, or Pima County, rather, in Arizona, and San Diego County in California were the first two places in the United States to develop lighting ordinances in favor of low-pressure sodium, in favor of downward reflecting shields on advertising lighting, and just limitations on how much light could be blaring up into the sky from commercial entities. So that was done over half a century ago, and it's been fairly successful. Dark sky reserves have also been maintained in some of the national parks in the United States, and there's an international analog of this through the International Astronomical Union. So there are dark sky reserves in various countries of the world that are maintained or supported by those governments, and the IAU as an international organization lends its weight to those and its stamp of approval, and that probably helps them get passed. But it's very hard to formally protect dark skies. Chile, which has many major telescopes and very dark skies, is protected essentially informally by the Chilean government, which does not allow rampant development or mining very close to the major observatories. The Chilean government realizes it's sitting on an incredible resource and a valuable resource, so it does its job protecting it. And the UNESCO, of course, has been involved as a UN agency in creating dark sky sanctuaries. If you imagine what a UNESCO site means, a sort of heritage site, some of those actually include dark sky regions, and there's a designation for that. So yes, there is some significant work internationally and within the major countries that house observatories to protect dark skies.
Excellent, thank you. The next question is from Afshan, who sent an email asking, what are the current challenges in understanding the nature of black holes, and how do recent observations, such as those from gravitational wave detectors, contribute to our knowledge of these enigmatic objects?
So the study of black holes has moved dramatically forward thanks to LIGO, Laser Interferometry Gravitational Observatory, which is now detected of order 550, dozens of black hole mergers and black hole neutron star mergers. And so we understand a lot more about black holes. And one of the enigmas of the LIGO results is how many of the black holes are quite large. The minimal mass of a collapsed massive star that generates a black hole is about 3.5 times the mass of the sun. But most of the black holes LIGO have studied are tens of times the mass of the sun, and the mergers it's seeing are between stars, each of which has a dozen or 24 times the mass of the sun. So LIGO is not seeing the lowest mass black holes that should exist, and you would expect in any reasonable distribution that would be more of the lower mass black holes than the higher mass ones. So that's a puzzle that's coming out of LIGO's results. Otherwise, you're testing general relativity in a very direct and exquisite way, and general relativity has passed those tests. So there's no problem there. That's an affirmation of our gravity theory. Black hole research is also deriving around how does energy get out of a black hole? Why do black holes, which themselves are black, become gravitational engines that can, in a case of a black hole at the center of a galaxy, outshine that galaxy by a factor of 1,000. It's an extraordinary amount of energy creation. So how that happens in astrophysics and physics is still a puzzle, and theorists have been working on it actually for decades. So there are plenty of black hole mysteries to still solve, and it's good that we have instruments like LIGO and Virgo, counterpart in Europe, we also a Japanese gravity wave detector, that are giving us much better data and many more observations of black hole mergers to work with.
Excellent, thank you. The next question is from Juan Carlos, who asks, I have taken one of the Coursera courses. My question is about Enceladus. Can you tell us what the discovery of hydrogen cyanide on Enceladus means, sort of what's the context for that?
Right, this is a very recent discovery. It was in Science magazine last week. So hydrogen cyanide is a critical, it sounds like an obscure exotic ingredient of chemistry, but it's actually not. In the chemical soup that led to life on Earth, hydrogen cyanide in its various interactions was a critical energy component in developing the first metabolism, basically. It's not key, just as phosphorus is a critical chemical element for developing and storing energy in biological life. So hydrogen cyanide, along with phosphorus and some other volatile chemicals, are facilitators of chemical reactions and facilitators of biological pathways as you develop the first chemical reactions that we would call biology. So it's very exciting to see it in Enceladus. It's not necessarily a surprise because the abundance of this molecule, even though it sounds a little obscure, is not super low. It's moderately rare, but not extremely rare. And so it accentuates, along with knowing that Enceladus has liquid water inside and local energy sources, it accelerates the possibility that there is indeed microbial life within that moon of Saturn.
The next question is from Dave McKenzie, who sent an email. Are there any plans to explore Ceres further before searching for life further out in the solar system?
Ceres, the biggest asteroid, first to be discovered in 1800, I think, 1801, is an interesting object, of course. It's hard to explore it directly because you'd have to go into captured orbit, as we did with Bennu and OSIRIS-REx. And so we're usually dealing with flybys of objects like that, heading further out into the outer solar system and then the Kuiper belt. And that's why we have pretty limited information about Ceres. So we don't really know its detailed chemical composition. We don't know if it's massive enough as a big asteroid on the level of some moons to have mild geological activity or potentially the ingredients for life. So we're really in a very early stage of research on the nature of Ceres.
Excellent. Thank you. The next question is from one of our live participants. Supreme Scientist asks, how do astronomers interpret the cosmic origins of humanity while acknowledging the complexity and distinctiveness of things like human emotions and societal constructs?
Astronomers sort of stick to the subject they're trained in. And so astronomers only really deal with how the nature of the universe and the ingredients of the universe in a chemical sense, in a physical sense, might have led to biology. And we've come quite a long way in telling that story. But astronomers don't have the skill set or the information, really, to talk about how life evolves to the level of complexity and cultures and civilizations. And so those sort of more detailed attributes of humans and human civilization are really the subject for other scholars to investigate.
Excellent. The next question is from Kristen, who asks, can you talk a little bit about or break down what's going on with Beetlejuice and its brightness fluctuations? What stage is it in now, and what can we expect from the rest of its lifespan?
Beetlejuice is obviously a red star in Orion, and it's a supergiant. And it's in an advanced and therefore fairly unstable stage of evolution where the fusion sources are changing and being exhausted, and the transitions to new fusion sources lead to instability and lead to fluctuations. Now, we've modeled these type of variations of fluctuations in computers, but in a very general way. For the specifics of a star like Betelgeuse, we would have to know a little more precisely its spin rate, its chemical composition, and of course its mass, to be able to make a very accurate model of those brightness fluctuations. So the theory of how the brightness fluctuates in the unstable stage late in a star's life is difficult theory, and it's even difficult to simulate. You need a supercomputer to do that.
The next question is from Yogesh, who got from the course, I guess, the chemical ingredients of the sun, planets, and humans are different why are the chemical compositions of the sun, the planets, and the humans different from each other when we're all made from the same nebula that collapsed to form the Earth Sun and that we evolved from?
Right. That's a good question. So the nebula that formed the sun was mostly hydrogen and helium with very small amounts of all the heavier elements. They're trace ingredients, basically. They're well under 1%, all of them put together. And of course, the other thing to remember is that in the solar nebula, 99.9+% of the mass went into the sun itself. So the sun reflects the chemical composition of the nebula that formed it, mostly hydrogen and helium with a tiny amount of heavier elements. However, in the formation process, the heavier elements could concentrate by accretion into rocky particles, initially just sand grains, dust grains, literally, and then eventually planetesimals and planets, while the radiation from the young sun drives away the light gas that most of the nebula is made of, the hydrogen and helium, by radiation pressure. And so you're left with outer parts of the solar nebula where there's a concentration of heavier elements, including rocky material. And so that, in a sense, is how you form rocky planets. And humans, reflect that composition in part. Life forms, and humans included, are mostly water. We're about 2/3 water, so H2O. But we always have a lot of carbon, calcium, potassium, nitrogen, and so on. And so outer parts of a solar nebula are sort of concentration, more highly concentrated in heavier elements than the sun itself. And that's really what makes that distinction between what we're made of and what the star is made of.
Excellent. Thank you very much. The next question, excuse me, is from one of our live participants. The official H96, several people have asked this question. Kaniz Fatima would like to know, is there such thing as a multiverse? And where does that idea come from?
The short answer is we don't know. Maybe, maybe not. That idea comes from modern cosmology, where if the Big Bang was a quantum creation event, which we think it was in the inflationary scenario of the Big Bang, then possibly there were other quantum entities contemporaneous with our infant universe. And that would lead to the idea of the possibility of other expanding spacetimes and therefore parallel universes. And that, in a nutshell, is the multiverse idea. So the multiverse emerges from quantum cosmology, from the idea of the universe as a quantum entity in its inception. Is a very difficult idea to test because these spacetimes are almost by definition distinct from our spacetime. They don't intersect it, or they're not a part of it. And so we would have to look like for some very subtle imprints of these other spacetimes, potentially only detectable in early universe observations, but nobody's even made the prediction of what to look for, let alone detected it.
The next question, excuse me, there's actually two questions, but one should be relatively easy to answer by answering the second one. So Kanis Fatima would like to know, is there really a real space station in space? And the related question from Michael Serrera is, there's a movie that's called ISS where the United States and Russia fight over the International Space Station. Is there any strategic value that the International Space Station holds?
It has strategic value because it's the only place where we can live and work in space, and have done so continuously for over 20 years. It also has strategic value in pointing to the fact that we can cooperate in space. Although the United States and Russia are at odds with each other over Ukraine and other geopolitical issues, they still are together on the space station. So America and Russia have not set aside their difference, but they've tabled them, relatively speaking, to be able to work on the space station. Now the Russians still are saying that they want to withdraw from the space station, and that without Russian support, the space station is in trouble because it needs the big space partners to keep it going, apart from all the Europeans that are involved, the Canadians and the Japanese and so on. So if the Russians pull out the space station is definitely in trouble. The Chinese are offering the Russians to go in with their space station, and that's probably where the Russians will go if they leave the International Space Station.
And then to follow up, so the space station is real.
Space station is real. It's been in existence for quite a while. I think citizens from 40 or 50 countries now have been on it. So these are many of the first astronauts for those various countries getting to the space station. It's been continuously occupied, as I mentioned, for I think 20 years. It's had peak population, I think, of 11 astronauts at once. Typical number is more like 5 or 6. It's always international, so Russians and Americans, Europeans, Japanese, Brazilians, and so on, working together. Very successful model for international cooperation in space.
The next question is from Albie. The question specifically is it possible that dark energy, the dark energy causing the expansion of the universe, might be some kind of turbulent energy?
It's possible, but the dark energy concept is not very well defined at this point. Dark energy probably is smooth because it's a function of space-time, and we know from various observations that space-time does not appear to have structure, interior structure. And so, it does not suggest turbulence because space-time is so smooth. So I think the simple answer is no, dark energy probably not a turbulent phenomenon.
Excellent, thank you. The next question is from Lysos. With all of the low Earth orbit communication satellites being launched, will we ever get to the point where Earth-based observatories become ineffective?
Well, we're getting to that point, but of course Earth-based observatories can house very much larger telescopes than the kind we can put into space. The James Webb Space Telescope, 6.5 meters diameter, is the biggest, by far the biggest space telescope ever been launched and successfully deployed. It would be very hard to put a bigger telescope in orbit. On Earth, we can build 10, 20, 30 meter mirrors and telescopes, and we are. So I don't think space is going to put ground-based observing out of action or out of business, just because the advantages of the infrastructure on the Earth, the much cheaper cost of building something big on the Earth, will dominate the future.
The Black Hole Girl, who's on with us live, asks, can you explain the concepts of dark matter and dark energy and how they influence the large-scale structure and evolution of the universe?
Yeah, the concepts are that dark energy is a form of matter, probably a fundamental subatomic particle that we haven't yet isolated, that exerts gravity because it has mass, the particle, but does not have an electromagnetic interaction. And it is responsible for holding galaxies together and for slowing down the cosmic expansion. Dark energy is far less well defined, appears to be a constant of nature, the same in every direction and at every epoch in the universe. It constitutes a form of energy that exerts negative pressure and so causes space-time to expand at an accelerating rate. And that's really all we know about it.
The next question is from Wendy, who sent us an email. Wendy Traver asks, is it thought that the Higgs boson, as the force carrier of the Higgs field, gets its own mass from the Higgs field? And wouldn't the Higgs field have to predate the other force fields for the universe that we experience?
Yes, the Higgs field does give mass to the Higgs boson, as it's called. And also, yes, in principle, the Higgs field was a pre-existing concept, or it was co-created with space-time itself in the Big Bang. It's not something that was added later. It must have been present at the creation.
Excellent. Okay, so that doesn't mean that it had to be there, but it was formed at the same time.
Right.
So I think that seems like a reasonable supposition. The next question is from Bernard, who asks, are there any observatories in either the United States or Canada that allow public members or amateur astronomers to visit at nighttime and allow them to do observations with their own equipment?
I'm not totally sure of this. Kitt Peak is able to host amateurs. Also, they have small telescopes at the Kitt Peak Observatory that are not always used by professional astronomers, and they're made available occasionally for members of the public for viewing. The members of the public can't control those telescopes. I think the best bet for running small telescopes and doing that kind of work are some of the more famous star parties outside of professional observatories. The Texas Star Party, held annually in the summer near McDonald Observatory. That's a famous example where there are literally hundreds of very high-end and very well-equipped and very automated amateur astronomer telescopes in operation, and people share tips. They share observing. It's open to everyone. They want public and kids to get involved. So that's a very dynamic, freewheeling observational astronomy experience and beyond what any of the professional observatories could provide.
The next question is from Crawley Enterprises, who asks, hi, Professor Impey, how do astronomers define life?
It's a difficult question because not even biologists have succeeded in defining life. If you look it up in different sources and books on the web, you may find about a dozen definitions of life from biologists and physicists and chemists and sometimes astronomers. The most specific definitions are very much keyed to our biochemistry. They're keyed to the idea of a cell as a container concentrating chemical reactions. They're keyed to the idea of information storage using a helix molecule like DNA or RNA. And they're key to a metabolism that's similar to those of the cells in a human body. But it's not clear that that's the unique definition of life. A more general definition of life might be just organization and transmission of information through chemical means, and the ability to evolve. That's key, because we think something that's living as opposed to something inert like a crystal, which can grow but doesn't actually evolve, that's a key distinction. And so most definitions include that distinction.
Priyanka Goswami is on with us live and would like to know, I wanted to ask about the effects of the upcoming solar storm on Earth and its environment when the sun reaches solar maximum in 2025.
People are worried about it because the high energy radiation will have a real impact. It hits the ionosphere and the magnetosphere of the Earth and causes cascades of high energy particles to be accelerated, which are almost certain to disrupt telecommunications and could take out power stations and even potentially the entire national grid of some countries, hopefully not a big one like the United States. That's a projection. The trouble is predicting solar maximums is historically not easy to do because they are variable in their strength, and we've not successfully predicted them within 30 or 40%. So the actual strength of the next solar max is not completely obvious, and it's in the end we're just going to have to watch it happen since we can't predict it very accurately.
Excellent. The next question is from an email from Sandra Gibson, who asks, says, "Aloha from Hawaii. I have a question on measuring time in high gravity or density environments and before matter was formed. How do you measure or define time in the early universe in conditions of high gravity or high density?"
It's a good question because, of course, time in the old and low density universe is an easy thing to measure. You can use mechanical devices, as we do, clocks, and you can use atoms themselves, the vibrations and oscillations of atoms, which is how atomic clocks work. And all that sort of falls apart when you go into the very early universe because there's no possibility of those devices existing in the very early universe except atoms themselves. So can you use atoms to talk about time in the very early universe? Possibly. But the nature of time in the very early universe may change under conditions of extremely high gravity. So that becomes a wild card in all the speculation.
Excellent. The next question is from, let's see, from Arif Roni, who asks, "Sir, is it possible for life to form on things other than planets and moons, like some kind of tardigrade in space? How might biomarkers be found at other places, like comets or asteroids?"
It's a difficult thing to speculate about life that does not exist on a moon or a planet. The best guess is that biology needs a liquid medium within which chemical reactions occur. That's the case on Earth, whether life was in a deep sea hydrothermal vent or in a small warm pond. Warm pond, as Darwin speculated. You need water. You need a rocky surface. You need chemical interactions. So life in deep space doesn't really satisfy these rules. And the bigger problem is the density in deep space is very low. So the level of interactions and the ability to build complexity, chemical complexity, which precedes biological complexity, is very limited. Fred Hoyle, famous physicist and science fiction writer, wrote a book called The Dark Cloud, I think in the 1950s, which speculated about an intelligence evolving in a sort of chemical electrical network of a protostellar cloud. That's pure speculation, and there's no sign from science that his idea could ever be real.
Excellent. The next question is from Faisal, who asks, "Are gravitational waves subject to deflection like light?"
Gravitational waves, since they are waves, I mean, they have transverse, longitudinal, and torsional modes of vibration. They are subject to refraction. So yes, it is possible for gravitational waves to be mildly deflected by large inert bodies of matter. Our ability to detect gravitational waves is not sophisticated enough to measure this effect, however.
Excellent, thank you. The next question is from LZL, who asks, "Computer models are incredibly useful tools for theory formulation in astronomy, but how reliable are they?"
They're only as good as the physics you put into them. So if you're simulating a universe, doing a model of galaxy formation or large-scale structure formation, you will only get out a sensible answer if the input physics is right, which means you have a gravity theory, you have ability to describe radiation and how radiation interacts with gas and plasma, um, and and then you have to put in dark energy and dark matter if it's a cosmology simulation. So simulations are very good, and of course the computer power is phenomenal, but they all need a certain asterisk attached to them, because if they're not tethered in a lot of real data, then their ability to predict something becomes a little dangerous.
Excellent. The next question is from Kaniz, who asks, what was the first galaxy discovered after our Milky Way galaxy?
The first galaxies to be discovered were the Magellanic Clouds. They're in the process, I would say, I will note, of being renamed, because Magellan, was a sort of arch colonialist who did not treat very well the island people that he encountered, or in the global south where he did some of his voyaging. And they are southern hemisphere companions to the Milky Way. And they were obviously known by civilizations going back tens of thousands of years, visible to the naked eye easily, not like M31, which is a challenge. So those galaxies have been studied or seen by civilizations around the southern hemisphere for centuries, millennia.
The next question is from JOHB, who asks, I was really curious, how does quantum mechanics stand in relation with relativity?
They sort of stand apart because they're very different theories. Quantum mechanics, a very successful theory of the microscopic world, dealing with the graininess of energy, with the limitations of the uncertainty principle, is very successful in predicting microscopic behavior. General relativity is a theory that deals with the geometry of space-time and uses that geometry as influenced by mass and energy to explain the force of gravity. And those two theories, they operate on very different scales, and they have very different conceptual bases. And so no one has successfully managed to combine them into a unified vision of the world of the very small and the world of gravity.
The next question is from Hernan, who asks, the Dragonfly mission has been postponed or delayed for 10 years, we are told. Is this due to a technical problem for getting there, or for having the right equipment? Is it a strained budget? What are the sort of underlying reasons for the delay?
It's very disappointing for many astronomers and space scientists that Dragonfly has been delayed. It's a very exciting mission. The Dragonfly mission is NASA's attempt to go back to Titan, a place we haven't visited for decades, and only ever had half an hour on the surface with the Huygens lander, and go there with essentially drone technology to fly around Titan and sample the ethane, methane, extremely cold lakes there and look for potential biology. So very amazingly exciting mission using modern technology. It's expensive and it's a long mission. So part of the delays come from the launch window. We know to get to Mars, there's a launch for using modest amounts of energy. There's a launch window roughly every 2 years. And so if you miss a Mars launch, you pretty much have to wait 2 years for the next optimal window. The windows are longer in the outer solar system, but the calculation is more complicated because all those missions use gravitational assists. So they will not head straight out to Saturn. Those missions will almost certainly use Venus, a massive interior planet, for a gravitational slingshot, and may use that multiple times or do multiple slingshots in the inner solar system before heading out. But the voyage is a long voyage, and so much of the delay is for getting the right orbital configuration or the launch configuration to get that far out in the solar system, because the travel time can be 4 to 6 years. And the other part of the delay, of course, is NASA's budget. Dragonfly is an expensive mission. It's not clear what the final price tag will be, probably $3 to $4 billion. And NASA's suffering right now from the eye-watering costs of the Mars sample return mission, where the price tag has ballooned to potentially $11 billion, which means the price of those samples, if you do the math, is about $800 million an ounce. It's pretty expensive stuff, those Mars samples. And that is sort of breaking the budget and breaking the bank at NASA, because NASA can only really do one multi-billion-dollar mission at a time. And so Dragonfly, unfortunately, as exciting as it is sitting in a queue that pushes it off probably a decade.
Excellent, thank you. The next question is from Michael Serrera, who asks, we recently saw that antimatter reacts to gravity the same way as regular matter. Assuming that antimatter follows the other rules of the universe, what, if anything, would change if antimatter was the normal dominant form of matter in the universe?
Right, so that was an interesting physics experiment of a few months ago that got some fair notoriety in the press, and rightly so. It's a foundational physics experiment. Nobody really expected antimatter to react to gravity in a different way than matter. But you can see why it's a difficult experiment because the gravity of big objects is easy to measure because it's a lot of gravity. The force is large. But you can't make large antimatter objects, and so you're dealing with antimatter particles individually. And the gravity of those particles or antiparticles is extremely weak. So you're measuring something really weak. And so it was a tour de force of experimental design to be able to show that antimatter in a lab situation operates and responds to gravity the same way matter does. So it is truly a mirror form of matter in the universe with opposite quantum numbers. And that's the main result of that experiment.
Excellent. And it is 11 o'clock, so we will take one final question, and then that will wrap it up for us for today. But then we will be back after the new year. Lawrence K. asks, I'm still confused by the double slit experiment. Is it possible that a single particle can create an interference pattern?
The double slit experiment, Young slit experiment from 1800, Thomas Young, a classic physics experiment demonstrating interference phenomena, and also based on the quantum nature of light and brought into the modern era, it demonstrates very beautifully sort of quantum uncertainty. So the situation is that when a large amount of light, trillions and trillions of photons, passes through a single slit and then double slits, an interference pattern will be seen on the screen behind the twin slits. And that's perfectly predictable in terms of the wave nature of light. The question becomes, what if you have one photon that goes through the first slit and then one of the two other slits and then hits the screen? How does that single photon know that it is to be part of an interference pattern where, in other words, rather than having trillions of photons a second, you just have one photon a second and you slowly watch the interference pattern emerge? And that conundrum has never really been fully resolved. We just make a statistical statement that we can say that the probability of where that single photon will land on the screen behind the two slits is described by the interference pattern and the wave nature of light, even though what you're talking about is a single particle. And of course, quantum physics is based on particle-wave duality, where the wave and particle descriptions are supposed to be and are fully equivalent. But it is one of the more puzzling issues from the quantum world. But it's real, and the experiment has been done, and it's been done by slowing down the photon rate so that you have individual photons traveling, and they do indeed slowly participate in an interference pattern. That's a good one to end with. It's basic quantum physics. A lot of good questions today, and I think we'll be back in the first week of January, and then we'll schedule the next couple. So everyone have happy holidays, however you celebrate them, wherever you are, and we'll be with you in a few weeks. Again, thanks to Matthew for facilitating.
Excellent. Thank you very much. Like I said, subscribe to our channel to hear about the next live session. Click the bell icon. Or join our listserv. If you scroll all the way back up in the chat, there's a Google listserv that you can join, or a Google group that you can join, and we send out announcements about the live sessions every week before we have them. So take care, everyone, and have a happy holiday season.